This projection is orthomorphic. Meridians are straight lines originating from the pole. Parallels of latitude are circles centered at the pole. The expansion is at the same rate in any direction from a point. We have already covered the graticule in discussing orthomorphism. As we said, meridians are straight lines originating from the pole. And parallels are concentric circles centered on the pole, with their spacing increasing as the secant squared of half the colatitude. The way that shapes will be affected is fairly obvious. Because of scale expansion, shapes and areas will be more distorted the further the distance from the pole. You can see that Africa looks too large compared with Europe and the northern part of the United States. And on this southern hemisphere chart, you can see that the northern part of the South American continent looks too wide. This chart has a convergence factor of 1. This leads to some interesting properties which we will explore in more detail in a later lesson. The parallel of tangency is actually a point of tangency. In this case, it's the pole, with a latitude of 90 degrees. The angle of the cone is, as with any cone, twice the parallel of tangency. The cone angle is therefore 180 degrees, which means that it has been flattened into a plane surface. The normal rules apply. The sine of 90 degrees is 1. This chart, therefore, has an n factor of unity, which is another way of saying that there is no segment missing when we flatten the cone. It is already flat. This means that the chart convergence is always equivalent to the change of longitude between 2 points, whatever their latitude. We can show it with this proof. This is a polar stereographic chart, looking down on the North Pole, with the Greenwich meridian coming in from the 6 o'clock position. Take 2 meridians, let's say 70 degrees apart. Because 1 degree of change of longitude is always 1 degree of chart convergence on this projection, there will be an angle of 70 degrees between them at the pole. Now draw a track joining them, not necessarily at the same latitude. Now, let's look at the geometry of this triangle. The internal angles of any triangle have to add up to 180 degrees. We have 40 degrees here and 70 degrees here, which add up to 110 degrees. Subtract this from 180 and that gives us 70 degrees here. The line AB is straight line track, and a straight line also has an angle of 180 degrees. So the supplementary angle, in other words the track angle at B, is 180 minus 70 degrees. This is a track of 110. The original track was 040. So the track angle must change by the amount of the chart convergence, which is also the change of longitude on this projection. There are just 2 more points before we leave chart convergence for this lesson. We shall return to it later. The first is that the meridians are straight lines. Therefore, chart convergence is constant all over the chart, whatever the latitude. The second is that there are only 2 places on Earth where 360 degrees of angular change of the meridian is equal to 360 degrees of longitudinal change. These are the North and South poles. So, chart convergence is correct only at either pole. Rhumb lines behave exactly like those on a Lambert's projection. Meridians are straight lines originating from the pole. Other Rhumb lines are curves concave to the nearer pole. It's obvious in the case of a parallel of latitude. However, any Rhumb line except a meridian will still be curved concave to the nearer pole. Great circles are also similar to the Lambert's chart in that they are concave to the parallel of origin. However, in the case of the polar stereographic projection, the parallel of origin is the pole. Look at the diagram. Again, it is looking down on the North Pole with the Greenwich meridian coming in from the 6 o'clock position. It shows 3 lines at 50 north and 3 more at 70 north. The blue represents a straight line on the chart. The green lines are great circles. And the red ones are Rhumb lines. This demonstrates that the great circles are concave to the nearer pole, but their concavity becomes less as we approach the pole. If we compare the great circles at 50 north and at 70 north, you can see that the great circle is closer to a straight line as the latitude increases. In fact, for all practical purposes, a great circle may be taken as a straight line at latitudes of 70 degrees or more. The primary use of the polar stereographic projection is as a polar plotting chart. Some meteorological charts also use it. And it can also be used for planning purposes on a global scale, as more than half the globe can be shown on a single sheet. Examiners will expect you to remember the primary use as a polar navigation chart. So, let's summarize what we've covered in this lesson. We looked at scale. It's correct at the pole. Elsewhere, it expands as the secant squared of half the co-latitude. Scale is within 1% of the polar scale out to 78 degrees latitude, and is between 1 and 3% of the polar scale between 78 and 70 degrees latitude. The projection is orthomorphic. All charts used for navigation must be. In fact, this one is both orthomorphic and perspective, and is the only one of our projections which is. We've seen the Graticule. Meridians are straight lines originating from the pole. Parallels are concentric circles centred on the pole, with the distance between them increasing as the secant squared of the co-latitude. We looked at shapes. They become more distorted as the distance increases from the pole. Chart convergence will be examined in slightly more detail in the next lesson. It's correct, which means the same as on the Earth at the pole. It's constant across the chart, and the chart convergence between any two meridians is equivalent to the change of longitude whatever the latitude. In other words, the n factor is 1. In considering Rhumb lines, meridians appear straight. But other Rhumb lines are curves concave to the nearer pole. Great circles also include meridians, which appear straight. But generally, great circles are curves concave to the nearer pole. However, they have less curvature than Rhumb lines, and they become nearer to straight lines as they approach the pole. They may be considered, for all practical purposes, as straight lines at latitudes greater than 70 degrees.